Good morning and welcome to today's webinar. We're just going to wait a few more minutes here to let people log in and we'll get started shortly. Good morning again and welcome to this morning's webinar. We'll get started in just a few minutes here as we let additional attendees log in. Again, welcome to this morning's webinar. I'd like to introduce our moderator for today's presentation, Anthony Drew.
Hello everyone and welcome to our webinar presented by Veolia Water Technologies and brought to you by Coal Publishing and Treatment Plant Operator Magazine, also known as TPO. My name is Anthony Drew and I'm the digital editor for TPO. This webinar is titled Evaluating Alternative Treatment Options to Eliminate the Need for Lime Sludge Disposal in Boynton Beach, Florida. The city's East Treatment Plant uses conventional lime softening followed by filtration, but it faced concerns that landfilling the plant's sludge won't be a long-term option. That's why it looked into alternative treatment options to eliminate the need for lime sludge disposal. Veolia's Actina pellet softener was pilot tested at the Boynton Beach East facility in the summer of 2020. A brief history of the facility will be discussed during this webinar, along with the results from the pilot testing and the subsequent full-scale evaluation. During the webinar, you'll be able to submit questions. In your control panel, you'll see a series of drop-down menus, including one titled Questions. This is where you'll submit your questions. At the end of the presentation, our panelists will answer as many questions as time permits. If the panelists are unable to answer your question during the webinar, they will follow up with you afterward. Now I'd like to introduce our panelists. First, we have Jake Hurley, Associate Engineer of Boynton Beach Utilities. He's a project engineer with 5 years experience in the water and wastewater industry. His work includes both construction and design of water treatment facilities. Also joining us today will be Tom Perry. Tom has 23 years in the water and wastewater industry and is currently the Director of Product and Market Development for Veolia Water Technologies. And with that, I'll turn the program over to Jake Hurley.
Thank you, Anthony. Today we're going to cover a brief introduction to the Boynton Beach utilities, followed by the Actina pellet softening process, the pilot testing results, a comparison of the operating costs, and finally a Q&A session. Next. Boynton Beach Utilities supplies around 120,000 customers a day with potable water. We also do sewer and storm water. We have 2 water treatment plants, an east water treatment plant, which is permitted at 24 MGD, and a west water treatment plant at 8 MGD. Here at the east plant, which is where we had the pilot process tested, we have traditional lime softening. The plant was originally built in the 1960s, and we have a lot of the existing infrastructure and equipment. Next. An interesting project we had complete in 2018 was a magnetic ion exchange process. We had this put in because we wanted to increase the capacity of the plant with a new raw water supply. This raw water supply had organics which required pre-treatment. So the pellet softening testing was done post the MIEX system. A couple of upcoming projects may be the renovation of some lime softeners, fluoride system, and we have existing ongoing power supply projects. Next. You'll see here on the left is a basic schematic for a Suez lime softener. You can see from point number 10, the excess sludge can be pulled. You can also use 11, the drainage pipe, depending upon how well the softeners are running. Over here on the right, you'll see a basic overview of how we are handling our lime sludge. Starts off in the softeners, where by gravity it feeds into our pumps, which shoot it over to the recovery basin. There it's mixed with backwash or any other water that we need to dispose of. It goes down and is pumped finally to the sludge lagoon. There at the sludge lagoon, we depend upon it percolating out or evaporating. Then it is dredged and hauled to the dry lime storage area, where eventually it is hauled off-site. You can see from the schematic, it's a large process, large footprint, and it's costly and time-consuming. Next. For some of the reasons, as I stated earlier, we have an aging plant. Both the equipment and infrastructure needs to be either worked on or replaced. Rising costs for lime sludge disposal. We've had a couple other utilities in the area say that their costs have doubled, even tripled, and it's a variable that we can't control. Our lime costs as well. Our lime supplier actually was very interested in this project because we wanted to make sure we were still buying his lime. And if we were to increase the capacity of this plant using lime softening, we would have a very difficult time with the footprint. We've also had issues during rain events. The sludge runs off-site. That requires costs for cleaning and maintenance. And as well as during dry times, it can blow off-site. So now I'm going to turn it over to Tom, who's going to cover the process description.
Thank you, Jake. So I'm going to go over some of the basics of the Actina process, just to give everyone a quick understanding of what it is and what it does. So it's a very simple fluidized bed reactor that uses a catalyst, which can be sand or calcium carbonate pellets, to basically act as a seed for the pellets to start to grow as the calcium carbonate precipitates out inside the reactor. It reduces calcium and some magnesium hardness while producing a reusable, easily dewatered pellet. So this is what a typical Actina reactor would look like. So you have the flow that comes in through the bottom. It will go through some flow strainers up through the fluidized bed into the flared portion of the reactor, then exit a common point at the top. So in the fluidized bed portion of the reactor, as I mentioned, is the catalyst, which is either sand or can be calcium carbonate pellets. But basically we change the pH at the bottom of the reactor to precipitate the calcium carbonate, and then it just starts to grow into pellets in the fluidized bed portion. And again, we produce this easily dewatered, potentially reusable pellet as our as our waste. So how is the influent flow distributed through the reactor? So at the bottom of the reactor, we have a plate that's at the bottom, and it has multiple holes in it. And in each of these holes, we have our flow distribution strainers. So again, you see a typical Actina reactor. If you take away this bottom portion and slide it over, you can see that strainer plate at the top, and then our individual flow strainers that are in the holes, basically in that plate. So again, the influent comes in at the bottom and is forced through these various strainers that help evenly distribute the flow. So the strainers that we use in Actina are specifically designed for pellet softening, and there's two key features to them. Obviously, the first one is their main purpose, which is to evenly distribute the flow through the fluidized bed portion, but in the manner that they're designed, they also allow for some material that may come in with the raw water to pass through and not create any clogging issues at the bottom of the reactor. So again, if you look at one of those strainers individually, this is what it would look like. It's basically in two sections or two pieces where you have a cap, and then you have the body of it, assuming everybody can see my cursor. So this lip here is what actually sits on this strainer plate. The bottom is threaded. We have a nut that holds it to the strainer plate. So the flow comes up through the middle, out through these holes. And again, this cap is on top. So the water goes through these holes and then goes through these openings that you see in the cap. So the picture below is an actual installation where you can see multiple flow strainers inserted in that strainer plate at the bottom of the reactor. So pellet softening is pretty straightforward, but having that even distribution of flow up through the reactor is pretty critical. So as I mentioned, you have to adjust the pH of the water coming in because you want the calcium carbonate to precipitate out of the water. So the way we do it with Actina is you can use either caustic or lime, and generally we're in that 9 to 9.5 pH, but it can be lower or higher, but it's a general range where we can operate to get maximum hardness reduction. So what we do is we bring the caustic or lime into what we call a removable spider or chandelier, which sits at the bottom of the reactor just above that strainer plate that I had just talked about. So again, we have a nozzle that has been specifically designed for pellet softening. And the main purpose is to equally distribute, whether it's the caustic or the lime, across the cross section of the bottom of the reactor, so it gets evenly distributed up through the fluidized bed and you get even precipitation rates through the reactor. But if you take the bottom of the reactor and you look at the blue plate that's in there, and you can see kind of the gold or brownish, tannish flow strainers that I had talked about before. Right above that, you see that circular support structure. And then on that structure, you see these nozzles that distribute or disperse the chemical. So the picture that just popped up, you can see what they actually look like for this particular chandelier. There's 3 nozzles. You can see that for each nozzle, there is a chemical line, again, whether it's caustic or lime, and then a carrier water line. So they come together in that nozzle under pressure and get dispersed out through the bottom of the nozzle. The number of nozzles you need on any particular chandelier is driven by the diameter of the reactor that you're using. So there may be more than 3, or there may be less than 3, depending on the size. And this is just a little bit of a more close-up look at what that nozzle looks like. Okay, so as we flow water through the fluidized bed, we're adjusting the pH. We have the catalyst in there, and we are getting pellets to start to grow bigger and bigger over time. So after a certain amount of time, you actually have to extract those pellets, because again, it's a fluidized bed. So you want to keep the pellets from getting too large, because then it'll have to be a challenge to fluidize them. So there's different ways that we can control when the pellets are extracted. You can continually measure the pressure above and below that strainer plate that I had showed you before, or you can actually do it just on a timer, whether it's a total flow treated or just an actual time lapse when to trigger a pellet extraction. But when you use pressure, we basically monitor the pressure above and below that strainer plate. So if you can see, hopefully, the weld marks from the strainer plate. So the plate is obviously inside the reactor. And then we have these pressure sensors above and below. So during commissioning, we'll actually establish a relationship between the difference between those two pressure points and the size of the pellets in the reactor. So again, you can use that differential pressure to trigger when the pellets need to be extracted. And when they are extracted, they basically can come out by gravity because you have a certain amount of head pressure above it. And if you need to move them to a certain distance away from where they're being extracted, you can have a pump that's in line to help move them to their final resting place, if you will. So when the extraction is triggered, it'll be pulled out through these extraction pipes. And there's usually multiple pipes, one on each side. And it's all automated. So again, it's either by time or by pressure. And once it's extracted, this valve you see here opens. It allows the pellets to be removed for a certain amount of time. The valve closes, and then you continue operating. So even during extraction, you don't lose the ability to treat water. Flow continually comes in while you are extracting. Okay, so how are the extracted pellets dewatered and handled? As I mentioned before, they're self-dewatering, so you don't need any mechanical dewatering equipment for the pellets. There's a couple different ways you can do it as far as how do you handle them. Most of the times it's just these simple bins that you can use as a kind of a temporary storage / drainage bin. You can do it either a single bin or you can do kind of a duty standby you see in the picture below. In the picture, the top picture, you can see the PVC pipe. It's basically coming out of the side of the building where the treatment plant is, and the pellets just get deposited into the bin. At the bottom of the bin is a screen, and there's 6 or 8 inches of headspace below that screen. So the screen retains the pellets above it and allows the water to drain out at the bottom portion of this bin. The one at top, you can see there's just a simple tarp that can be pulled over the top of the bin to keep the rainwater out. And the one on the bottom, you can see that it's actually got an overhang from the building to accomplish that same goal of keeping the rainwater out. Get a little closer in on this double bin setup. You can see in the middle of the picture a PVC pipe that is where the pellets would come from the reactor. This PVC pipe is movable, so you can distribute the pellets throughout the size of the bin, and you can swing it in between bins, as I mentioned, kind of like a duty standby. You can notice on the bin in the foreground where you can see the water that's draining out of the bottom of the bin. So these bins are sloped from the back forward, and again, as you fill them with extracted pellets, the water begins to run off the pellets almost instantaneously. For larger facilities, and this is really both based on a treatment capacity and or the amount of hardness you're actually going to be removing, you may need something larger than these bins, but I would say for a majority of the projects we do, these storage bins are more than enough. A couple quick videos for you. So this first video is an actual operator extracting the chandelier / spider. So this is actually a shorter version. The whole thing took probably about 5 minutes to pull up from the bottom. So this is kind of the tail end of that exercise. You can see the chemical feed tubing that's going down to the nozzles that are on the chandelier. So this is something you can do periodically just to see what's going on with the nozzles at the bottom. Once you get it up to the top, you simply can just swing it over the top of the reactor and set it down on the grating next to it, so that if you need to do some maintenance on it, or you just want to inspect it, you can do that. So to pull it out, you can shut the flow off going into the reactor. But when you lower it back down, you do need to have the bed fluidized so that it reaches the bottom of the reactor. And at the bottom of the reactor, there's just some simple feet that you know when it's all the way down at the bottom. So the second video is actual pellet extraction. So again, this is that 2-bin example I had showed you. You can see there's just a simple piece of rope tied to the piping where they can move this piping to different areas of the bin to evenly distribute the pellets. So remember, there at the bottom, underneath these pellets is a screen that retains the pellets but allows the water to drain out. So you get drainage top to bottom, but you'll see here, if you take a look to the left-hand side of this video, you also get just straight drainage off the top of the pellets, just because they do dewater so easily. So you can see to the left-hand side, as more pellets are extracted, you can see that the water starts to run off very quickly. Pans out to the front, and then you can actually see how the water exits the bottom of the bin through these drainage ports. So you can capture this pellet drainage water and put it back into the head of the plant. You can send it to the sewer. It's generally a relatively small portion, anywhere from 0.1 to 0.2% of the forward flow would be your pellet wastewater, if you will. Okay, real quick, go through some of the testing results and just kind of a general summary of the pilot testing. So we tested for 4 weeks at the Boynton Beach facility. We tested on multiple combinations of wells. We operated with both caustic and lime. And throughout the testing period, we monitored and sampled for hardness, iron, alkalinity, turbidity, and UV 254. Just a quick picture of the setup. The picture in the upper right-hand corner is our control panel skid, and on that skid we have chem feed and some other items, and then the larger picture to the left is the actual pellet reactor. So our pilot uses the same flow strainers and the same pH adjustment dispersion nozzles that our full-scale facility would use. So it's very representative of full-scale operations. And kind of midway in that larger picture, you can see the pellet extraction piping, and we basically just extract into a very simple bucket that retains the pellets but allows the water to drain off. And in the lower right-hand side, you can see some pellets that were actually produced during the Boynton Beach testing. You probably noticed that they're not white like the original ones I had showed you. They have iron in their raw water, so the iron will precipitate out with the hardness, and it will have an impact on the color of the pellets. So the treatment goals, we're shooting for a softened water total hardness in the range of 80 to 120 milligrams per liter. We also monitored the iron reduction rates, and then obviously we wanted to establish what our best caustic and lime doses were for achieving that softened water total hardness goal. So during the testing period, this was the average influent water quality. I won't read it all off to you, but the influent total hardness was about 243, and total iron was 0.24 milligrams per liter. So this is just a collection of data when we were operating with caustic. And this is both from the initial optimization effort that we did, as well as some other data points that were collected over the course of the testing period. So the blue diamonds you see are total hardness results based on the titration method that the Boynton Beach operators do. And then the green ones are field TNT kits that we used throughout the testing period. But as mentioned before, the goal of the testing was to be in that 80 to 120 milligrams per liter of total hardness in the softened water. So that with caustic, we were able to achieve that with a pH around 8.5 in the Actina reactor, and that corresponded to a caustic dose of anywhere from 80 to 90 milligrams per liter, depending on the influent alkalinity level. For lime, again, similar collection of data. There was some initial optimization we did, and then we ran under different circumstances throughout the testing period. But if you block out that 80 to 120 softened total hardness range with lime, we were in the pH range of about 9.5 to achieve that, and a lime dose of anywhere from 155 to 165. Some additional testing results. Again, I already mentioned the pH that we use for the different pH adjustment chemicals, but the iron, as you can see, was below 0.3 in the raw water. So we just really monitored it over the course of the study. There was some wells that had higher iron levels notoriously. And again, there was a blend we were using throughout the course of the testing. So we ran with caustic probably 60% of the time, and with lime maybe 40%. So there's less overall data, but in general, when we were using caustic, we were able to reduce the iron up to 75%. And we didn't do anything different. It was just the iron precipitates out with the calcium carbonate. From an alkalinity standpoint, between caustic and lime, so you can see in the softened water, we had higher levels of alkalinity in the softened water when we were using caustic, which was no big surprise. But that, considered a good thing if you are trying to minimize corrosion in your distribution system. You can get both the hardness reduction you're looking for, the iron reduction potentially, and a higher alkalinity in your effluent. So that was a good all the way around with caustic. From a turbidity standpoint, you can see with the caustic, the softened water turbidity was considerably less. Again, not a big surprise. The lime slurry has some fine particles in it that do make their way through the fluidized bed. So, obviously, the lower your softened water turbidity, the better your filters will perform in regards to time between backwashes and overall production rate. So we also took a lot of samples and just filtered them through a 0.45 micron filter pad under a vacuum, just to see what potential impact the filtration step would have. And throughout the testing period, we saw a significant reduction, in that filtered sample. And again, it's not intended to represent what a full-scaled effluent filtration turbidity would be. Again, this is just a single pass through a 0.45 micron paper. So it's just really a comparison between the different pH chemicals we were using. And we also timed how long it took for 300 mils to be filtered at the same time. So it was really just more of a looking at as a comparison between the two pH chemicals used. And last but not least, we have the UV254. Again, this wasn't a focus of the testing, and we didn't get the benchtop instrument to the site until towards the end of it. I would just say that, as we noticed, as can be expected, as the iron in the influent changed, the UV254 changed with it. But we did see consistent improvement of the UV254 after softening and then after filtration as well. Okay, so based on the pilot testing results, we estimated how much pellet production would be needed or would happen, and then how much catalyst would be consumed for Boynton Beach based on these two scenarios, which was an average daily flow of 8 million gallons a day, and then a total hardness reduction of 60%. So under that scenario, under those two scenarios, we estimate that when you operate with caustic, with Actina, you're going to produce about 4.5 cubic yards per day of pellets. When you operate with lime, it'll be about 6.3 cubic yards per day. And the reason it goes up with lime is because you're actually adding calcium to the water with the addition of lime. So the picture to the right, you can see what the pellets from Boynton Beach look like after they had a little bit of time to dry. So when you compare either of those numbers, the 4.5 or the 6.3, to what Boynton Beach currently produces in sludge of 14.5 cubic yards per day, you can see a pretty significant difference. And the biggest difference between those numbers is really just the fact that these pellets can be easily get to 95% solids versus 30 or 40% solids with thickened lime sludge. So the biggest difference there is just the amount of water that remains in the waste. From a daily catalyst use, when operating with caustic, we assumed about 1,300 pounds a day, again at 8 mgd, and then with lime, about 1,900 pounds per day. What's kind of unique about pellet softening is you can actually take your waste pellets and crush them and reuse them as catalysts. So the amount of catalyst you would need would be the same, but you can actually potentially eliminate the need for sand, excuse me, if you reuse your pellets. Okay, I'm going to throw it back over to Jake to go over some O&M cost comparisons that were derived from the pilot testing results.
Thank you, Tom. As you can see here, this is our existing lime softening annual chemical and sludge handling cost. You can see lime is right around $500,000. The most important thing to note is the handling and dredging cost at around $130,000. That can range pretty drastically depending upon how greatly we're using our East water treatment plant or the weather. Next. Here we have an estimate using caustic. This was our most cost-effective option. You can see the greatest difference is in the hauling and dredging costs at around $38,000. In addition, you can see the catalyst or the sand. That cost can be limited if you invest in crushing the effluent. Next. Here's an estimate with the lime. Similarly, hauling and dredging, substantially different than what we have now. Also, big difference with the pellet softening. As I showed in the schematic before, we are moving the sludge in multiple locations, multiple times, a lot of time and effort on that. Whereas with the pellet softening, the hauling and dredging could be potentially a lot less. Next. So you can see here in the picture on the right, we have our northern solid contact clarifier basin. It's currently out. I was inside of it last week. There's some substantial metal repairs that we'll need to do. So these costs, it's more of a 5 to 10 year band-aid, and depending upon how the system's working, we may need to do a full replacement. So just a repair can be in the hundreds of thousands of dollars, but to do a full replacement of the two systems could be in the multi-million-dollar range. Another issue that we have is that the concrete work around that area and some of the piping and structure, it is from the original plant. So if we were to have to do a full rehab of the infrastructure and the equipment. Obviously, once you get into the multi-million-dollar estimate, that's what sparked us to look at the pilot testing and to see if there are any alternatives for us. And that's a summary of our work. Now I'm going to turn it over to Anthony for the Q&A session. Thank you.
All right. Thank you to Jake and Tom for the informative presentation. It looks like we do have time for a few questions, so I'll start with this. What is the typical duration for Actina pilot testing?
Yeah, so as I had mentioned, we were at the Boynton Beach facility for 4 weeks. But I would say typically we could, be done in 3 weeks. Some are shorter, some are longer, but I would say on average 3 weeks is a good estimate to plan for at any location.
Okay, next question. What is the most common driver for municipalities to evaluate pellet softening?
Well, our driver at the city, you can see it in the top left photo, was our sludge lagoon. It's filled with water half the time, it's expensive, and we wanted to see if there was a way to limit it.
Okay.
Yeah, let me add to that too, Anthony. So I would say for us, the biggest driver is either a current or a future disposal limitation, and whether it's the lime sludge or it's if it's a reverse osmosis plant and they have a brine disposal. So far, it's usually been driven by some restriction either happening now or anticipated in the future that will impact the way they get rid of their current waste.
Great, thank you. Next question, what is the next step for the Boynton Beach pellet softening evaluation?
Well, on the city side, we have to get our estimates for a complete replacement of the equipment so that we can compare a construction cost estimate for both lime replacement or pellet softening.
Okay. Our next question is, how often do the nozzles require cleaning?
So the nozzles, make sure I wasn't on mute. Yeah, so the nozzles on the spider, generally as an overall, the reactor as a whole is an annual maintenance where you would take it offline and you can drain the water out, and you can actually either put the pellets or the media that's in there into your storage bins, or actually put them into another reactor if you have multiple reactors. But generally it's an annual event or cleaning where you take it offline and try and do your best to get rid of any scaling that has accumulated. But in regards to the spider and the chandelier, I think we recommend probably every month or two just to pull it up and take a look at it and just see what's going on. If you don't see any issues with performance or anything like that, that would require you to do it sooner. But if it's just kind of something we would recommend every month or two just to pull it up and take a look at it.
Okay, thanks. Our next question, do you add anything to improve the solubility of lime so you do not get deposits?
We do not. Generally, like when we, at the Boynton Beach pilot, we actually ran with the slaked lime slurry that the existing facility uses. So Jake, I don't know if you guys do anything special there to enhance that solubility of the lime. I don't think you do, but maybe you do.
I don't believe we do.
Yeah.
Okay. Our next question. What is the typical detention time to grow the proper size pellet to remove from the fluidized bed?
So that really has different drivers to it. Obviously, if how close you're operating at your design capacity, and then also how much hardness you're removing through the system. I meant to point it out when I was showing you the some of the data from the pilot testing at Boynton Beach, but they have a pretty wide range of operating pHs with either caustic or lime. So if for some reason you need to get more hardness reduction, you can increase the pH in your reactor, or vice versa. If you don't need as much, you can decrease your pH in your reactor. So it's really driven by how much hardness you're removing. But in general, I would say, you know, you're going to extract pellets maybe 2 or 3 times over a 24-hour period.
Okay. Next question. Do you need to replenish the media at any point?
Yeah, so the catalyst is, you know, whether you use sand or crushed pellets. So when you extract the pellets, the catalyst will be kind of in the middle of the pellet, if you will. So if you're using sand, what sand is in the fluidized bed is kind of the nucleus, if you will, of that pellet. So as you extract those pellets, you are removing some of the media with it. So in general, you know, if you're extracting 2 or 3 times a day, you'll probably need to add additional media once or twice a day. So it's not something you do every time you extract, but it's maybe every 2 or 3 times you extract, you have to add some fresh media back into the system.
Okay. Next, we have a influent hardness of 450 to 530. Is this feasible for our plant?
I would say yes on 2 conditions. It depends on obviously the level of softening or the amount of hardness you're looking to remove, and also the breakdown of your total hardness. So I think at Boynton Beach, the total hardness was, I think, around 80% calcium and 20% magnesium. So the pellet softening will get a majority of the calcium hardness and a small portion of the magnesium hardness. So it depends on what you're looking to achieve from a total hardness reduction, and also how much calcium hardness is in your influent.
All right. Next
Hopefully that
question.
answers the question. Yeah.
Can the sludge lagoon be eliminated altogether?
I'll let you take that one, Jake.
Ideally, yes, we would try to use a system similar to if you had a sludge thickener and then use the hopper method, a system that didn't require us to, because the pellet is mostly dewatered, we wouldn't need it to evaporate out or percolate. So as long as we didn't increase the capacity of our plant drastically, then we would be able to ideally eliminate the sludge lagoon.
Okay.
So Anthony, I see one there looking for the hardness level at the east water plant. So I'm just going to back up, try not to make anybody nauseous looking at this slide. I'm going to go back to, yeah. So then one of the questions is, what was their hardness level at the east water treatment plant? So Again, here you can see the average influent over the 4-week testing period with 243 total hardness, and you can see the breakdown between the calcium hardness and the magnesium hardness at the treatment plant.
All right. Next I have, what happens to the solids when water upflow is stopped?
So, like if you had to shut down, like any water plant would, over whether it's a daily shutdown or whatever, it's not an issue. You just stop the flow to the reactor, the media goes to the bottom. And again, if you remember kind of the way our flow strainers are at the bottom of the reactor, they're also intended to help retain the media in, above that strainer plate when there's no water in the system. So you can leave it there for a certain amount of time, say maybe 2 or 3 days, before you have to expand the media again. If you're gonna have it idle for an extended period of time, we would suggest that you either expand it every so often or actually drain the water and the pellets completely out of the reactor. But one thing you do when you shut down, regardless if it's for 2 hours or 2 days, you do flush the system so that the higher pH is no longer in the reactor. So you would just bring in raw water, if you will, that isn't adjusted, that isn't pH adjusted, so that when the pellets are sitting in there again for a couple hours or a couple days, that it's not, a pH of 9. But it can easily be started and stopped for a decent amount of time without any issues.
All right.
And Anthony, I see number 10 on there is, if you don't mind, I'd like to answer. So
Sure.
there's a question about, can it be used to treat brine from reverse osmosis? It mentions a desalination plant, but I know we did some testing earlier this year in Colorado, where we actually were taking RO brine from a groundwater treatment plant and used Actina to soften that water to a point where they would actually be able to reuse it, put it back into the plant and actually send it out to the distribution system. So I would say yes on that question. Can it be used for brine recovery from a desal plant?
All right. How does the sludge pellet volume differ between using caustic and lime, and what kind of lime was used?
Jake, I'll let you answer the type of line. I think it's just quick lime, but I'll let you answer that. It's like slaked quick lime.
Yeah, I believe so. I can confirm that.
Yeah, they just bring it in. It's pretty typical at Boynton Beach. It's a pretty typical setup where they bring the lime in. They have they have grit removal, and they basically bring it in and put it into a slurry, and then pump that slurry to their reactors. But the biggest difference is, because you're feeding lime, you're actually, not only are you adjusting the pH, but you're adding calcium to the water as well. So as you add more calcium, you're going to remove more calcium with the pellets. So you'll actually see about roughly a 50% increase in the volume of pellets you produce when using lime versus caustic, just because of the fact that you're actually adding adding calcium to the water when you feed a lime slurry.
All right, looks like we have time for about 2 more questions here. I'm going to go with this one. Are you planning to landfill the pellets, or do you have a selling or reuse option? In the case of Boynton Beach, does the iron in the pellets prevent them from being sold or reused?
So we have been looking for ways to dispose of. We've even looked at seeing whether we could help with putting them on the beach, or but we haven't confirmed any resources yet. So the cost that we would estimate would be just the cost to haul it to a dump.
And yeah, and there is some options out there. It's going to be kind of regionally driven. You can use, I've been to some of our facilities in France where the groundwater plant is surrounded by farmland, and it was actually the video I showed of the pellet extraction into that into those bins. But in that particular instance, the farmers take their pellets monthly, and I think they just use them for fill on their farms. But that particular plant just gives them away to the local farmers. You can use them for fill. You know, there's I've heard that there can be used for, say, like landscaping bricks and things like that. Not so much for, you know, construction concrete, but you know, for something simple like a landscaping brick or something like that, they can be used to help manufacture those. And to the point of the iron, so I think that if you probably have more options with a nice pretty white pellet than, you know, something that's discolored. But I don't think, you know, whether it was fill or some of those other things, if that would really impact your ability to use them.
All right, and our last question, how is the media added to the unit?
Right. So it can be a couple different ways. It just needs to be into a slurry. So if you say you're using sand as a catalyst, you can convey it into a mix tank with a mixer, and then you can pump it out of there, and it can either go into the top of the reactor and just fall straight down, or you can inject it into the side. There's also, you do like an eductor where the sand falls into an eductor, and then it's just got some plant water under pressure that kind of flows past the bottom of a funnel, and that can wet it and carry it to the reactor as well. So a couple different options, nothing too, you know, overly sophisticated, but it would be just like adding you know, a slurry to any other process.
Great, thanks, Tom. With that, it looks like we're just about out of time. So thanks again to today's presenters for the webinar. Those of you in the audience will receive a recording of today's webinar and a follow-up email with instructions on how to reach out to our presenters with more questions. Any questions we didn't get to today will be answered in a follow-up email. Thank you all for joining us today, and that concludes our webinar.